starting off with Newton, inventor of calculus. Some people argue it's Leibniz. See, I knew Alex would, so Alex and I studied undergrad maths together, and then he hates Newton for some reason. So, then we have Grassmann. Many of you know him. He basically invented linear algebra and these vector spaces. Then we have Alan Turing, Turing machine, modern computers. Frank Rosenblatt, he was actually a psychologist in America. He invented in 1950 the perceptron, which most people consider the first artificial neural network, which is effectively what we use today in all of our machine learning. Skip about 60 years, we get to a significant amount of computational power, where we get to Alex with AlexNet. He was one of the first people to train, instead of things on CPUs, he was like, okay, these graphical processing units, they can do parallel processing, they can do way more calculations. Let's try on GPUs. And this was a fundamental breakthrough in AI, where suddenly we able to do a lot more computational power. He worked for Google for a bit and then quit. And then Jascha, one of the scientists who invented diffusion models, this is effectively what we use for generative models, so like things like ChatGPT or DALL-E, which are to create images. Effectively, you remove some of the data, it predicts what replaces that data, and then through iterations to predict it. And then Jakob is one of the 8 scientists that wrote Attention. I can't actually remember the full name. Attention is everything. Is that the
Attention is all you need.
Yeah, attention is all you need. That's correct. Thank you, Peter. He invented transformers, which is the fundamental block of all modern large language models. Of course, I've missed a lot of contributors, but this is just a brief history of AI. Okay. So when I talk about AI, I actually mean machine learning, and when I mean about machine learning, I actually mean neural networks. Because no one actually gives, no one cares about linear regression or just regression distribution neural networks, effectively. They're like very okay tools for approximation. They're black boxes, but neural networks are far by the most dominant tool of this case. I say it's 10 to the 3, it's actually about maybe 10 to the, well, it's about 10 million parameters at least for a modern neural network. How do neural networks work? Effectively, watch the 3 blue, 1 brown video series on it. It's far better than I could do. I actually watched this before my PhD interview and it got me through, so that's all you need to know. So as a brief introduction, so you send a picture of a dog, you send it through some nodes, that's what these are, you have activation layers, and you say it predicts it's a cat, so it predicts, okay, so these are some eyes, these are some ears, it predicts it's a cat, and then we say, okay, it's not a cat, you update the nodes between the different layers, and then until it is convinced that it's a dog, and then you say it's a dog. It's obviously far more complicated. This neural network would definitely not be able to classify a dog in this case, but yeah, just watch the videos. Okay, so there's lots of different types of machine learning tasks. We have supervised learning, so that's when you give it. So you say this is an image of a dog, and it learns consistently this is what an image of a dog is. You have unsupervised learning. So say you really like Taylor Swift, you're a node in this diagram, and then other people who like Taylor Swift, like Sabrina Carpenter, for example, you know from your Spotify rap from today. And then you cluster in this unsupervised way. You have generative learning, so this is a famous picture from DALL-E, which is similar to diffusion networks that I use. It's when you remove data and it's able to, you put a prompt in, it's able to generate things from scratch. And this is reinforcement learning, most famously with AlphaGo, but this is AlphaZero, this is chess game, this is known as an immortal game from the 1850s, any of you play chess. Basically it plays against itself sufficiently and it learns how to do things. Obviously this is like it's a summary. There's semi-supervised learning, there's contrast learning, where we mix all of these different ways together. Okay, so different domains. There's statistics, that's the boring part. This is like anyone who has like a GCSE in maths can do. So we just move past. Automation. Since when you tell the algorithm, okay, you get a +1 for scoring a goal, you get a -1 say for not scoring a goal, and it learns through this process. This is how chess works, and these automated things. We have natural language processing. This is your ChatGPT. It's able to learn from tokenization and temporal data what is happening. And then computer vision, which is predominantly what my PhD and this talk is on, is you can see from an image, so say for example, here you have a car or a person, you're able to track it over long periods of time across the video. Okay, so now, brief history of neurosurgery. I don't know if are there any doctors in this room. Okay, yes. Okay, so you guys can correct me, because this is not my expertise. I believe modern neurosurgery started in the Middle East with Avenka. I probably pronounced that incorrectly. Then we move on to human anatomy, and then for my work, antonym is endoscope. I'll come back to this. It's interesting that it was actually done 200 years ago. And then the modern neurosurgery, these are the two fathers. Harvey Cushing, he came up with Cushing's disease and a lot of other ways of doing endoscopic surgery. And Victor Horsley, Sir Victor Horsley, he worked in Queen Square, again around the corner where I get all my data from, about 100 years ago. And the first microsurgery was done by Carl Orloff, who actually was taken the 1912 Olympics in tennis, so overachiever. And Raymond Damadian, he got the Nobel Prize for inventing NMR, or the MRI scan, and that's just more representative of like modern advancement in technology with MRI, CT, robotics, and now artificial intelligence. So neurosurgery, or medicine in general, is quite a young subject comparatively, so there's lots of improvements to be made. Okay, so my talk is going to be predominantly on minimally invasive surgery, also known as keyhole surgery. Effectively, so this is laparoscopic cholecystectomy. It's when you inflate the stomach, you make 3 holes in the patient. You have one that allows you to see what's going on, and then you have 2, which are the instruments that you use to take out the gallbladder. These guys have done everything first. Because it's general surgery, there's way more data available across the world. So everything I say in this talk with regards to AI, we are second to do, or I am second to do, but it's all in neurosurgery. So pituitary tumors. Okay, so the pituitary gland is a pea-sized gland found off just the base of the brain of the hippocampus. It controls most of your hormones, growth hormones, thyroid hormones, prolactin, so that's like reproductive hormone. Very, very important. If something goes wrong with it, it causes these hormonal imbalances, but less intuitively, because it's in an atomically dense area, so it's right next to the optic nerves. It can put a lot of pressure, and so it can cause visual impairment as well. About 20% of people will have a pituitary tumor in their lifetime, which is quite, seems quite a lot, but most of the time it's not an issue. But about 1 in 1,000 people will have symptomatic problems with it, and yeah, well, that means that approximately 1 person in good enough will have it, which I do know is to be true, approximately. Okay, so endoscopic surgery, so there are many ways to try and remove these tumors. So you can try and do drugs, you can try and do radiotherapy, but surgery is the most effective way it's been found. This is when you go through the nose to cut out the tumor. So you have an endoscope, so that's the camera with some light. So it allows the surgeon to see, as you can see on this side. So from a few slides ago, you see it was invented in the early 1800s, so it's taken 200 years effectively for us to have the camera sufficiently small enough for us to get through the nose to get to this time. It's for microadenomas, so that's just a fancy word for tumor. So that's 10 millimeters or lower. It's effective about 99% of the time. For macro, so that's 10 to 40 millimeters, it's effective the majority, about 98% of the time. And then beyond that, it's not as effective. So about 70% of the time, we get gross tumor removal, where that means that most of the tumor is removed and the patient can live normally. Unfortunately, it's a very it's a very difficult surgery. The surgeons claim it's like eating through chopsticks through a matchbox. Because you can see through the entry here, I don't know how, yeah. You've got a very small hole, and you're trying to fit both the endoscope and an instrument through. It's difficult surgery. And globally, so in the UK and US, the adverse effects aren't as big, but in less socioeconomic goes wrong. So that's either a form of diabetes where you can't urinate properly, or so your brain's in the vat, so cerebrospinal fluid can leak out if you don't close the things properly, and you get infection. Or more severe effects, about 1% of the time, it can cause either a coma or death or visual impairment if you accidentally cut the carotid nerve or the optic nerve. Okay, so the AI assisted part. So this is a statistical one. This is the most boring part of AI. I won't talk about it too much. For example, so this is when we're trying to get the patient data and the type of closure that they use, and whether they'll be able to predict whether they're going to have this cerebrospinal leakage. So in this case, for example, tissue glue was found to be effective. This is a very boring use. It's a real use of AI. So here, for example, we're trying to extract the tumor. This is the sphenoid bone in front of the pituitary gland, and the blue part is known as the sella. The yellow is the clival recess. The top two are the optic nerves, and the bottom two are the carotid arteries. So the AI is able to detect relatively well, about with 80% dice score, or accuracy, as some of you may call, whether the sella is there or not. And so this is a difficult process. I have a demonstration here. So imagine this is the tumor, and you have a piece of paper. So this is the sphenoid bone. It's effectively trying to predict through this piece of paper, where this ball is. And I don't know how about you guys, but it's quite a difficult task to do, because you're only telling from the impressions that it's making on this piece of paper where this tumor is. And if you're a few millimeters off, you can cut off the carotid artery or the optic nerve. You don't want that to happen. So I don't know how many of you guys would want to arrest someone else's life on how accurately you can take out this table tennis ball. So through this automation, we're hoping to improve that fact. Currently, they do use a thing called a stealth pointer, so that tracks with the MRI scan that they have beforehand and tells you approximately where it is, but this will hopefully do it in real time. Okay. This is just a sample, so we've got 36 neurosurgeons, from people who have 0 years of experience to consultants. We showed them an image of just an image with no data, and an image, this black line with the AI prediction, or the model prediction. And we improved the dice score again, you can think of that as accuracy, from 71% to 78%. And more interestingly, it made that someone who had 0 years of neurosurgical experience, so people in F2, if you know the UK system, were as good as consultants. So that's consultants who have 20, 30 years of experience to detect the sella were as good with the AI as someone who has 0 years of experience. This most recently got published in Nature, so please read it. That's probably the most effective use of AI that we have, and we're trying to implement it in real time in, firstly in Queen Square, hopefully in other hospitals later. Okay, another use, step recognition, surgical step recognition. So surgery is split into several steps. So firstly, the pituitary surgery is split into 3 phases. So the nasal phase, when you go through the nose, the sella phase, where you're trying to extract the tumor, and then the closure phase, where you're closing up all the holes you've made. But then more granularly, in these phases, you can have multiple steps. So, for example, in this sella phase, we're extracting the tumor. You have celotomy, where you're removing the sella. You have durotomy, where you're removing the dura, and then you have the tumor excision, where you're removing the tumor itself. And we're able to detect these various stages automatically. And this is useful because we're able to send this data to surgeons, junior surgeons, and then it shows significant improvement. So OSATS is a subjective way of measuring how good a surgery is. It stands for Objective Structured Assessment Training, I think. So in this study, we spent a year. Every month, they would be given the analytics telling what happened in these various steps, or what the AI predicted happened in the surgery with the step annotations. And we had a control group where where they didn't give this data, and a group where they were given this data. And we've shown that with this AI data, or the step recognition data, we improved the OSAT scores from 7.3 to 7.8, which was with p-value statistically significant. So it shows that, so effectively it shows that if you have something that's significantly deviant, so say you say the tumor excision phase is much longer than you would predict, then the junior surgeons will be able to go into the surgery, click on the video where they think, or where the AI predicts to be much longer than we expected. They can analyze it, whereas a surgeon who doesn't have this AI model then would have to watch the whole video effectively, and it's a much more inefficient use of their time. And so this was able to significantly improve performance. So hopefully we can get it into a lot more surgeons, a lot more hospitals. And effectively, because the surgery is, well, this model is trained on about 100 videos, whereas an average surgeon maybe does 10 of these surgeries per year. So we're able to condense a lot of information, decades worth of ability or experience into these models. A second use of this is through the operation notes. So at the end of a surgery, your surgeon will spend 10 minutes or so writing what they've done. This can often be inaccurate because after approximately surgery is about 75 minutes. The surgeons forget. Honestly, a lot of them just don't care about writing the op notes at the end. So this can analyze the video, determine what's happened, write it automatically for you. We have also used LLMs, so large language models, to do this as well. And an accuracy significantly improves. So this was for 57% accuracy, 77% with the AI assistance. So that's another use case. Okay. And the final use. Okay, so instrument tracking. So we're able to track the instrument, see where it's gone, and through this tracking data, so there's two main use cases actually. So the first is you can tell the scrub nurse beforehand, say 5 minutes before, okay, the pituitary rhombus coming up next, can you get this ready? It improves efficiency. It means that the surgeon doesn't shout at the nurse, and it also means that the patient gets through a lot faster. It also means we're able to correlate it with surgical ability, and find out how this motion of the instruments is able to produce better results. So our model, with 87% accuracy, will tell whether you are a consultant or not. And the main factor for this was the ratio of total procedural time to instrument to visible time. Effectively, that just means like how efficient are you using the instrument itself. It's pretty obvious that if you use the instrument more efficiently, you will be a better surgeon. But it's good to actually prove it with data. Yeah. Does anyone actually care about the AI stuff? Because I can explain that. I think only Douglas is the... Okay, Peter as well. Effectively, we use CNNs, LSTMs, some UNet. We use DeepNet V3 a lot as well. Some temporal smoothing, some pseudo labeling. But you can talk to me after if you actually care. Anyway, that was the end. It's my website. You can follow me on various social media. We can do a demonstration